We are going to learn about physics, what it means, the very word. We're going to learn that measurements is one of the main activity that physicists do. And after that, we are going to introduce significant figures, or in short, sig figs, and how to figure them out, differentiate them from non-significant figures. Let's start with physics. What does it mean? The word, where does it come from? It comes from Greek, has entered Latin, and after Latin has entered English. It means nature or natural things. So when we say physics, we are referring to the nature. And physics is the science of understanding nature. So people have started to understand the relationship between different phenomena so that they can harness the power of nature into their favor, so that we can have a more comfortable life, a less laborious life, so that you can press a button, make coffee, press a button, communicate with someone across the planet. So that's physics. Now, one of the main things physicists do is measurement. They measure different phenomena, measure the temperature, measure the mass, measure the volume. So all these measurements have to be done using certain principles so that the measurements are precise. Imagine if you have to do a sensitive measurement, for example, on a piece of equipment that, like a bar, that has to be used somewhere in the engine of an airplane. Right? Now, if you don't measure this precisely, that could cause the lives of hundreds of people. So that's the sensitivity of this topic. You have to done these measurements, you have to follow certain principles, scientific measurement, precise measurement. We're going to learn about that. So when you want to measure something, you're going to have to use certain tools. To measure the length, we use a ruler. So these are the tick marks on the ruler. You can see it starts from 0. And let's say these are all in centimeters. So starts from 0, 1, 2. If I ask you, when you're given this tool to measure the length of something, one thing you have to know is what is the precision of the tool that you have available. The precision of this ruler right now, what is it? So for answering that, you have to figure out the smallest increment on this measurement tool. And the smallest increment on here you can see is 1 centimeter, from 0 to 1, from 1 to 2, right? The smallest tick marks here, the distance between them is 1, always 1. So that's the smallest increment of this measurement tool, which is the same as to say precision of this measurement tool, of this ruler. Now, suppose you are given a bar and you want to measure its length. So you put one end of the bar at 0, and this is the other end of the bar, ends up here between 5 and 6. So the number that you have to report, you have to follow a principle. What you gonna say? Are you gonna say this is just 5 centimeter? And then they use this bar in the airplane wrongly and the airplane crashes and you lose your job? Are you gonna say 6 centimeters? What you gonna say? So here's the principle. When you're measuring this, you notice that here's the end of the bar between 5 and 6. So the length of the bar, if I show it with L, is definitely larger than 5, but it's also smaller than 6. It's between there. But with this ruler, the smallest length you can measure is 1 centimeter. It's like 1 centimeter increments. So how can you say something between 5 and 6 where there's no tick marks here? That's where your estimation comes in. This is now the next level of precision you're gonna add to it. That's your estimation. So up to 5 centimeters, L equals 5 centimeters. We read that directly from the measurement tool. Now there's no more tick mark. We have already passed the precision of the measurement tool. Now we add one more digit, one order of magnitude smaller, our own estimation. So 1 order of magnitude smaller than 1 centimeter increments is what? Let's calculate. So 1 over 10 times the precision of the ruler, which is 1 centimeter, equals 0.1 centimeter. So your estimations have to be on the order of 0.1 centimeters, or 0.2, 0.3, all the way up to 0.9. That's where your increments of your estimation, which you have to add to it to follow scientific measurement principles. So the length equals 5 point. This is now what you are adding. 5 point, your estimation. Now this is purely based on your own estimation. So someone else could guess something and you could guess something else. So you can see this dashed dotted red line is already, if we assume the middle is over here, it's even surpassed the middle. So I'm going to estimate it as something like 5.7. That's my estimation. You could say, no, I disagree with you. It's 5.6. That's also okay because it's purely estimation and we are already surpassed the precision of our measurement tool. Okay, let's give it another example. So imagine the end of the bar is not here. The bar is actually longer. Again, we put the one end at 0 and it comes all the way to here. Now what? So again, you record what you get from the measurement tool that you have available. So I can see it's coming right at 7. So we're going to record length equals 7. Now it's time for your own estimation. You must add your own estimation always when you're doing scientific measurements. So 7 point. Now what you going to say? Well, it looks like it's right on 7. So what we going to say? Well, my estimation is 0. 7.0. Right? Even though it's 0, you still have to mention. Even 7.0 exactly equals 7 in mathematics, but in scientific measurement, these two numbers are a little bit different, and the difference is what they communicate to the reader. When I see 7.0, I understand that the measurement tool that they have used to measure the length of the bar, the smallest increment on that measurement tool is 1 centimeter. When I look at this number, 0.7.0. If I look at this measurement, just 7, that means that the scientific measurement tool that was used to record that number 7 is a ruler, for example, this green ruler down here. And the tick marks on that are just from 0 to 10. That's it. So that digit communicates that the measurement tool has been used is this one, which is ridiculous. Like, there's no ruler like that, really, that has from 0 to 10 centimeters. So we learned about estimation that has to be added to your measurements. Let's see another example. Here we have a more precise tool because you can see here down is centimeter, up there is inches are listed. So imagine again, you have a bar, you put one end at 0 and the other end goes up to here. So the first question we ask ourselves is, what is the precision of this tool? What is the smallest increment on this tool? And if you look closely, the tick marks between each one of the big ones, each centimeter here, there are 10 divided into 10 parts. So then if 1 centimeter on this device is divided into 10 parts, so 1 centimeter divided by 10, that's 0.1 centimeter. That is the precision of this tool. Precision of the tool. What does that mean? That means our own estimation has to be on the order of 1 order of magnitude smaller than that. 1 power of 10 smaller than that. So that means if the precision of the device is 0.1, now our estimation has to be multiplied by 1 over 10, which is 0.01 centimeter. Okay? So that is going to be our own estimation on the order of that, 0.01. Now let's measure the bar. So we notice that the bar comes off right here, just short of 8. And it surpasses 7.5, right? It passes the middle of 7 and 8. Also, it passes the first tick mark. And it looks like it comes right on the second tick mark after the 7.5. So from the ruler, I read L equals 7 point. The second tick mark means 7.7. Second tick mark after 7.5, right? So that's the 7th tick mark after 7. That means this red line here, red dashed line, is like 0.7. Okay, so L equals 7.7, and that's the number we get from the measurement tool. We haven't done any estimation of our own yet. Here's our estimation come into the picture. Now, I can see here, from my perspective here, this is just right on the spot, right on 7.7. So the next digit that is supposed to be our own estimation, I will guess it's 0, 7.70. Now, someone else could look at this and say, no, in my opinion, it's 7.71. That's totally acceptable too, because it's up to us. Now, the next digit, which is our estimation, is up to us. Okay, another example. Let's see. Now, suppose this bar doesn't end here. It's a longer bar, goes up to here. So we know already the precision is 0.1. We know our estimation has to be on the order of 0.01. And looking at measuring the bar, looks like it comes right at 9. So length equals 9. But because the precision of the ruler has of the order of 0.1, so we put 9.0. And now your estimation comes into the picture, 9.00, because in my opinion, that's just right on 9. Someone else again could say, no, in my opinion, is 9.01. It's a little bit further than right on 9, so that's why. But they're both acceptable. Your estimation is up to you. Okay, that's how we measure things. Now, this was the length, but if it's volume, if it's any analog device, that's how you do it. You read from the measurement tool, and then you add 1 order of magnitude smaller digit as your own estimation. So your estimation here, these numbers, 9.00, even though in mathematics that equals 9, there's no difference between 9 and 9.00. In physics, in science, in chemistry, these figures, these zeros after the decimal point, are significant. And they matter. They communicate something. They communicate the precision of the measurement tool that it was used to measure that length. So that brings us to the next topic, which is significant figures. That's what we were talking about. The zeros after decimal point, they are significant. So we go to the next topic, and that is sig figs, significant figures. There are certain rules to find out significant figures. Rule number 1, non-zero digits, non-zero, are significant. Non-zero digits are significant. For example, if you have a number 23, that means it has 2 significant figures. If you have a number 117, that has 3 significant figures, right? So non-zero digits are always significant. If you have a number 1.23, so how many non-zeros? There are 3, so that's 3 significant figures. That's rule number 1. Rule number 2, sandwiched zeros are significant. Sandwiched zeros are significant. What does that mean, sandwich zeros? That means the zeros that are in between non-zeros digits. Look at this example. I have 2002. So these zeros here, these 2 zeros are sandwiched between 2 non-zero digits, so they count as significant. So overall, this number has 2 sandwiched zeros and 2 non-zero digits, so overall it has 4 significant figures. Look at this, 2.01. Again, this 0 again is sandwiched. This one. So we count, there are 2 non-zero digits, 1 sandwiched 0. So overall there are 3 significant figures. Rule number 3. Trailing zeros after decimal point are significant. Trailing zeros, like the tail of the number. Trailing zeros after decimal point are significant as well. Check. So let's give an example of trailing zeros. So we had these numbers after decimal point, right? Pay attention to this part. It says after the decimal point. Trailing zeros after decimal point. So 2.01000. All these zeros, even after the decimal points, are still counted as significant because these are trailing zeros after decimal point. And as we saw earlier, they communicate the precision of the measurement tool used to record that number. So now this number overall, how many sig figs it has? Pause the video and answer. 3 trailing zeros, 1 sandwich zero, and 2 non-zero digits. So that's 3 plus 2, 5, 6. 6 significant figures. Another example could be like 0. Or like 20.100. Again, these are 2 trailing zeros that they count as significant figures. 1 sandwich, 2 non-zero digits. So here we have 1, 2, 3, 4, 5 sig figs. Excellent. Let's see the 4th rule. Trailing zeros with no decimal point are not significant. Trailing zeros with no, in a number with no decimal point, so this is not counted as significant. Cross. Like what? Look at this example. Trailing zeros with no decimal point. So 2120. Okay, this is a trailing zero. This is at the end, at the tail of the number, and there's no decimal point in this number, in this figure. So how many decimal points there are here? Just the non-zero digits, 3. The trailing zero in a number that doesn't have a decimal point does not count. Like another example, just 2000. How many sig figs it has? It's just 2. It's just one, sorry. This digit, number 2, is significant. So there's one digit that is significant. So that's rule number 4. Let's see the last rule. Leading zeros are not significant. Leading zeros are not significant. Not sig. Like what? So if you have a number like 100, if you put zeros to the left of it, that doesn't change the number at all. It's still 100. Zeros to the left, they're not counted. They're not significant. So this number, how many sig figs it has? The leading zeros, they don't count. The trailing zeros in a number that doesn't have a decimal point, they don't count. So this number just has one significant figure. Look at this number, 0.001. How many significant figures there are? Pause the video and try to answer that. Leading zeros, so we know this first of all, this non-zero digit, it counts. But the leading zeros, they don't count. And we don't care if there's decimal point here. These are all leading zeros, all in a row, without interruption. They're not sandwiched, nothing. So this figure here has also one significant figure. Another example, 0.0020300. How many significant figures are here? Again, leading zeros, they don't count. Non-zero digits, there are 2 of them, they count. Sandwich digit, it can. Sandwich zero between 2 non-zeros can't. Trailing zeros after the decimal point. Pay attention that we have a decimal point here, and these zeros are counted as trailing zeros after the decimal point. So they also count. So overall, we have how many sig figs here? 1, 2, 3, 4, 5. 5 sig figs. That's how we figure out significant figures using these 5 rules. Very easy. Next, we are going to, in another video, we are going to learn how do we do operations, arithmetic operations like multiplication, division, addition, subtraction, using significant figures. And if we have, for example, we're multiplying 2 different numbers with different number of significant figures, we're multiplying them by each other, what's the result that we have to record? The result has to have how many significant figures? We're going to cover that in another episode. Hope you enjoyed it. Let me know if you have any questions.